Let's just jump right into it. We are looking at a massive, fundamental shift happening right now at the very edge of frontier AI. We're moving away from AI that just sits there and generates answers to your prompts towards something entirely different. We're talking about AI that can recursively improve itself. This is a game changer. And today we're breaking down exactly why this evolution requires a totally new approach to how we actually design and govern these systems. So here's the crucial question. If a system can diagnose its own weaknesses, spin up its own training tasks, and literally update its own code, well, it possesses immense power, right? But it also means it can permanently embed and amplify its own mistakes. So the question isn't just, can AI generate better answers? We already know it can. The real question is, can AI participate in a stable improvement loop where it diagnoses weaknesses, creates experiments, verifies results, and updates itself without completely collapsing its own accuracy and safety? To unpack that massive question, we're going to run through 6 key areas in this explainer. First up, the new AI frontier, followed by the very real danger of recursive drift. Then we'll dive into the energetic paradigm architecture, how to govern the improvement loop, the concept of true discovery beyond mere search, and finally, how to build stable and auditable AI. All right, section 1, the new AI frontier. Let's go ahead and break the illusion that frontier AI is just a really smart, static chatbot waiting for you to type something out. You see, we're looking at a massive leap from static answer generation to a circular, self-improving, recursive intelligence loop. Think about this static model. The AI spits out an answer and a human evaluates it. Simple enough. But in the recursive model, the AI becomes this continuous closed-loop engine. It evaluates itself, it runs experiments, it updates. It's almost like an organism rewriting its own DNA on the fly. Now, it's really important to grasp that recursive intelligence isn't just one single magical breakthrough capability. It is a highly complex systems problem. It requires these 8 connected functions to operate perfectly in sequence. Think about the sheer mechanics here. The AI has to spot its own flaw, turn that flaw into a training task, search for evidence, generate a hypothesis, build a test, verify the results, check to ensure it didn't drift, and finally, update its models, tools, and memory. If literally any single one of those steps fails, the entire loop is compromised. Which brings us to section 2, the danger of recursive drift. Because we really need to look at what happens when that complex 8-step loop starts to break down. And this is where things get genuinely alarming. You see, a recursive system is essentially an amplifier, and it doesn't just amplify intelligence, it amplifies whatever enters that feedback loop. So if you have a weak objective, it's going to create highly distorted goals. If you have a weak verifier that rewards false progress, or maybe a contaminated benchmark acting as a training signal, the AI is going to confidently and rapidly optimize for completely the wrong outcomes. We call this phenomenon recursive drift. See, an ordinary error is just a bad answer. It happens once, and it's over. But recursive drift, that is a reproductive error. It's a mistake that sneaks into the improvement loop, survives a weak verification check, and then actually reinforces itself as if it were progress. So ironically, the stronger the model gets, the more efficiently it can exploit its own weak supervision. That makes recursive drift an incredibly dangerous compounding problem. Moving on to section 3, the energetic paradigm architecture. Because to stop this drift, we really need to shift our mental model completely away from just making models bigger. Enter the energetic paradigm, or EP for short. This is a proposed reasoning, control, and discovery architecture for self-evolving AI. EP doesn't just view AI as some isolated brain in a jar. Instead, it treats intelligence as a structured flow, incorporating goals, constraints, paths, feedback, losses, verification, resources, and consequences. Rather than just asking, hey, did the system improve? EP demands that we ask, what actually changed? Why did it change? What evidence supports it? What constraints were preserved? What risks were introduced? And, crucially, will the next iteration reproduce the same direction? By breaking down hard problems into measurable states, things like sources, sinks, paths, barriers, and constraints, we basically turn this mystical black box AI growth into strict, auditable systems engineering. Notice how problem decomposition stops discovery from turning into just uncontrolled random idea generation. On top of that, deductive path selection forces the recursive system to map out its explicit reasoning. A hypothesis absolutely must connect a premise to a mechanism, to a prediction, to a test, and finally to hard evidence. A plausible idea isn't automatically a useful discovery without that rigorous path. All right, section 4, governing the improvement loop. Let's see how this all builds into the actual heavy-duty mechanics of systemic control. Look, in a system that writes its own rules, control can't just be some final safety filter slapped on at the very end. It has to shape the actual process that creates improvement from day one. You need objective control so the AI knows its true north, path control to enforce logical reasoning, constraint control to keep safety limits active 24/7, verifier control to check the checkers, escalation control, meaning if the AI hits a high-risk decision, it actually pauses for human review, and finally, recursive control to oversee that entire self-updating loop. And honestly, perhaps the most critical layer in all of this is verification governance. Why? Because verifiers can and do fail. A verifier might measure the exact wrong thing or reward superficial style over actual truth. It might have hidden blind spots, or it might just drift over time. Because of this, the EP framework mandates that the verification system itself must become an object of rigorous verification. We're talking constraint audits, adversarial reviews, and executable tests just to keep the verifier strictly honest. And this applies heavily to multi-agent systems. You know, we constantly hear about throwing multiple AI agents in a room to solve a problem. But simply adding more agents without a functional architecture, that just duplicates work, amplifies agreement errors, eats up compute, and hides underlying contradictions. Under EP, agents have strict functional roles. A decomposition agent breaks the problem down. A constraint agent actively hunts for violations. A drift auditor constantly checks if the overall loop is veering off course. The goal here isn't just more agents. It's better coordination through very specific, structured roles. Let's jump to section 5, true discovery beyond search. Because we need to apply this heavy-duty control architecture to the highest stakes application out there, scientific discovery. It is so important to understand that finding information just isn't enough. Search is not discovery. An AI system can rapidly retrieve billions of documents, parse literally every research paper ever written, and still completely fail to identify a meaningful question. True discovery requires something deeper, scientific taste. It requires the ability to evaluate causal mechanisms, novelty, feasibility, testability, and long-term value to actually push a field forward. EP takes that elusive, almost magical quality of scientific taste and treats it as something that can be partially structured through strict evaluation criteria. Before an AI even pursues an idea, it has to answer the hard questions. What is the causal mechanism? Which constraint kills this idea first? What hidden trade-off makes this entirely useless in the real world? Can this even be falsified? This rigorous filter stops the AI from falling into the novelty trap, which is just generating thousands of highly unusual, complex ideas that are literally impossible to ever test.
Which brings us to our final part, section 6, stable and auditable AI. Let's focus on how the AI model and its surrounding harness have to adapt together.
You see, deployed AI is a coupled system of models, tools, memory, prompts, APIs, and tests. Everything we collectively call the harness. And this EP architecture is really the only way to govern their co-evolution without losing stability. As the core models get vastly smarter, old harnesses might actually become severe limitations, or even worse, they might entirely miss new failure modes. So the real challenge is how the model harness system adapts as a pair, guided by a framework like EP that strictly monitors their combined energy flow and preserves long-term stability. So here's the ultimate takeaway from this explainer. Faster, more capable AI, that's not the actual goal here. Controllable, verifiable, and recursively stable intelligence is. As we cross over into the era of self-evolving systems, we really have to ask ourselves, are we just going to close our eyes and blindly trust that stronger models will figure it all out? Or are we going to demand the disciplined, energetic architecture required to actually govern them? It's a huge question to think about as this technology accelerates. Thanks for joining me on this explainer, and definitely keep questioning the frontier.